lecture, we derived how Eggman pumping may influence vertical motion. So if we have somewhere a cyclonic or anticyclonic circulation, then Eggman pumping will act on that at the low levels, will cause for a low pressure system convergence, for a high pressure system divergence, and that will lead within the boundary layer then that it adds up in the boundary layer and leads to vertical motion. And this vertical motion can be important. That's the reason we will use this fact today in today's lectures, because that can trigger remote adjustments to vorticity fields and so on. Now, what we will discuss today is the remote adjustment to a localized heating. Well, we have discussed the ENSO event already intensively. So what's happening if we have a warm patch somewhere in the Pacific? So for example, if we have this situation here, a warm anomaly like in 2015, 2016, then we may expect typically that there are adjustments all over the world to this. Locally, we have discussed what is happening locally. The Bjerknes feedback is working, so there's a positive feedback nearly instantaneously working in the equatorial Pacific, but there are also remote teleconnections. Now, some of them we were actually already able to explain, because if you look at this, for example, for a warm episode, so that is El Nino event, in winter, in boreal winter, we have this warming in Alaska. And the opposite is the case for La Nina event. We have the cooling in Alaska. Now, if we go back to these maps here, so when we have this El Nino event, what is happening, we've seen that this will lead, this increased heating in that region, and we have discussed this extensively, will lead to positive vertical motion in the case of an El Nino event. So we'll get rising motion that is compensating then for the heating. The heating has to be compensated for something. The most efficient way in the tropics is this rising motion. And when that hits the troposphere, maybe we can look at this here. When this vertical motion hits the troposphere, it is forced to diverge because it cannot very well intersect the troposphere. There can be interactions with the stratosphere. There are interactions also with the stratosphere, but that is a more complicated story that we won't discuss very much. But the basics is that the stability in the stratosphere is so high that the vertical motions are strongly damped. So there has to be, due to the continuity equation, there has to be upper level divergence. Now this upper level divergence, if we think about the vorticity equation, acts as a Rossby wave source. So that generates Rossby waves. These Rossby waves propagate into the North Pacific. And for example, one of the nodes is this, that it strengthens the Aleutian low. And this is here for the surface, but this will be, it can be observed that in the exotropics, this response is is everywhere. You can go up to 5 kilometers or up to 10 kilometers. You will find a very similar circulation response. So in order to explain the warm anomalies in Alaska, we can simply think, okay, there's a southerly flow here that will probably advect warm air from more southerly, from warmer regions into the colder regions. It's a very simple explanation. So sometimes there can be very simple explanations for teleconnections. But we are in this lecture more interested in the rainfall adjustments that are typically much more complicated to explain. There are many rainfall. You see, there are wet there are many rainfall adjustments in remote regions. There are wet regions and dry regions and so on. And we also have things in the boreal summer season, the famous Enso-monsoon relationship, and so on. There are many more actually than listed on these maps. These maps are continuously updated for new teleconnections that are identified and that are found to be robust. So in these maps, you would only find the most robust teleconnections probably. But there's already, I think, there are many more than listed in this map actually. So today we want to a little bit to revisit what can be mechanisms for those remote rainfall adjustments, where for many purposes we are very much interested in rainfall adjustment, particularly in many tropical countries. Economies are dependent on rainfall, and so that is an important topic. So the lecture today is kind of taken from a study that we did not a long time ago, just to revisit. That wasn't a very new study, but we just revisited some of the mechanisms that have been proposed already in a very, very simplified setting to better understand what can go on as an adjustment to a localized heating anomaly. What can be the mechanisms for the remote adjustments? And so I've listed here as A to E mechanisms that have been proposed for remote adjustments. Now we have discussed already that in the region where we have the sea surface temperature perturbation, like El Nino, we expect a destabilization of the atmosphere because we warm from the bottom. We warm the lower troposphere through the sea surface temperatures. That will destabilize. And so that will lead to these adjustments that we have been discussing. There will be increased convection on average, and we get the mean motion. Then there's heating, and this heating goes into the upper troposphere. And then we have also already discussed that will probably trigger Kelvin, equatorial Kelvin, and Rossby waves that propagate the signal in the upper troposphere everywhere else. So one of the hypotheses is based on this. So probably outside the region where we have this strong sea surface temperature perturbation, we may expect, due to this propagation of the signal of this the atmosphere has been warmed locally, and then this signal is propagating along the tropics. That may stabilize the atmosphere outside this region where we have the heating, because we quickly propagate this warm anomaly in other regions where the surface probably is more damped at the surface, where the sea surface temperatures, they are not so much influenced. It's much easier to influence the temperatures in the free troposphere. So that may stabilize the atmosphere everywhere else in the tropical regions. This is one very, very accepted mechanism how a localized sea surface temperature perturbation can affect remote rainfall perturbations. It just suppresses rainfall due to a stabilization of the atmosphere. Then the next mechanism is also, we've also discussed already in principle. We have this, we may get upper level convergence in the regions outside the heating, surrounding the heating, which should compensate for the upper level divergence in the heating region. So the spatial average about you can show that the spatial average about the horizontal divergence in the stationary state using the continuity equation should be 0. So whenever you have whatever is coming up and diverging must be converging and coming down somewhere else. And okay, we may, this is a very bad sketch, but here maybe the heating region where we have this upward motion, and then this is diverging, and then at some other regions there may be convergence and downward motion. Now we have also already sketched this possible mechanism before in principle, like for example here. So there may be regions where you get sinking induced by this rising motion. And this sinking motion, because we have always this approximate equilibrium between diabatic heating, which could be mainly condensational diabatic heating, at least what concerns the wet tropical regions that we are considering. So the sinking motion should be compensated by a reduced, if we have moisture in the atmosphere, should be compensated most effectively by a reduced convective or in general latent heating. Not latent heating, but heating through to reduced condensation. There could be other mechanisms. If we are in a dry atmosphere, we have a problem, because then the sinking motion cannot be compensated by convective heating or by large-scale condensational heating reduction. So we have to have radiative processes that must compensate from this. But if we are in a wet region where it's on average raining, then that could be a mechanism. So this is another very, very well established, well understood mechanism. Then, for example, you may induce flow changes in remote regions. We have seen that the Gill response was already suggesting that there are remote responses, wind responses, not local, but remotely. So the Kelvin and Rossby wave, they carry the signal everywhere, and we get wind responses remotely. Now, if these wind responses are such that, if we assume that there's an orography, so if the wind is forced to flow against an orography, it may be forced to rise. So we get another mechanism for rising motion in that case. And then that would lead to, again, to condensation and to increased heating and rainfall in that region. And the mechanism that we have derived in the last lecture, we have the possibility that if we generate vorticity in the free atmosphere, vorticity outside this heating regions, again through flow changes that are spread by our wave propagation everywhere, also the Rossby wave propagation that propagate to the north, that may lead to Eggman pumping. So Eggman pumping could also play a role. We could have vorticity somewhere, and the Eggman pumping would act such that it generates vertical motion at the top of the boundary layer. That vertical motion may be able to trigger then convective rainfall and so on, or the opposite may act to suppress convective rainfall. And another mechanism that has been mainly proposed for the relationship between El Nino and the monsoon, the South Asian monsoon, is that we haven't discussed this yet, but one of the driving mechanisms for the South Asian monsoon in summer is thought to be the contrast between the much more strongly warming landmass and the less warming Indian Ocean. So the landmass has less heat capacity, so can warm up much quicker than the Indian Ocean. So this thermal gradient between the Indian Ocean and the Asian landmass is thought to drive at least parts of the South Asian monsoon. So the air will try to flow then into this warmer region. But we will discuss this in the next lectures in more details, this mechanism. Now, if we spread our El Nino warming then in other regions, that may reduce this temperature gradient. So if we have a warming that is mainly located in the tropical belt, but less if we go to the north or to the south. So if this warming kind of enters the Indian Ocean, we may modify this meridional temperature gradient induced by the land-sea contrast. And so that has been also proposed to be a mechanism how we can modify rainfall in the monsoon regions, because we modify the basic mechanism for the monsoon itself. Okay, so many things. Now, what we want to do is to simplify this view, because these are very, on average, very complex mechanisms that are very difficult to pinpoint using observational data sometimes. So what we want to do is we want to use an idealized model simulation to try to pinpoint some of these mechanisms. Oh, and I've forgotten one mechanism actually that I have drawn kind of here, which is a very important mechanism, in particular in the extratropics. It's complicated though. So imagine we have a low pressure somewhere, like our Aleutian low on average. So there's a low pressure, let's say in the Pacific, low pressure here. Since our flow obeys some basic conservation laws, and we have discussed this already for adiabatic reversible flow, which is not an exact approximation, but may be applied sometimes to get the basic picture. So potential vorticity was one, and the entropy or the potential temperature was the other. If our flow going around a cyclone, we can go back to the very first picture actually that we were looking at. If our flow is obeying the conservation for potential temperature, then it will tend to move along lines of within this constant potential temperature here. So whenever air is flowing to the north, if it conserves potential temperature or entropy, it will tend to rise. Whenever air is flowing to the south, it will tend to sink if it conserves approximately at least potential temperature. So if it's adiabatic reversible motion, then we get other mechanisms also coming into play afterwards. But as a first step, we can assume that the flow tries to conserve this potential temperature. If that's the case, then we will always have let's go back. Then we will always have on this side of this would be a cyclone in the northern hemisphere. We would always have on this side of the cyclone, on the eastern flank, we will always have rising motion, because the air flows from the south to the north. So conserving potential temperature, the air would rise. But on the other side, the air would sink, because it goes from the north to the south. So we will always have this tendency. And that is another mechanism to induce vertical motion that then can trigger all kind of other processes. We will discuss this in more details in the next section, but in the next lecture. Not the next, but the one afterwards. But I just want to give you a hint already. If we look, for example, this is the southern hemisphere, this is the northern, let's concentrate on the northern hemisphere summer, boreal summer season. If you concentrate, we can concentrate on both here on the North Pacific and the North Atlantic. So we have this also in northern boreal summer. We have a large anticyclone sitting here over the oceans mainly. Large anticyclones over the ocean that then lead to our trade winds. And the shading, the color shading here is the rainfall. But look how the rainfall distribution look like if we look here. It's very dry in California and very wet on the other side, on the would be the East Asian monsoon region. So there's a huge contrast in wetness between these two regions. And the reason is that on this side, we have the sinking motion induced by this law that the air tends to obey potential, in this case, potential temperature conservation. and here the opposite is the case. And we find exactly the same in the Atlantic, where now this is characterizing what we call Mediterranean climates. So we get these dry conditions in the Mediterranean, and the wet conditions in the North American monsoon region in summer. And in the Southern Hemisphere, we would have exactly the same. So this is quite a powerful mechanism also. Okay. And this will be included also in what we are discussing now. Now, what we want to do is we want to use a model, a numerical model, to simulate those mechanisms. And the model that I'm using is a model that I'm often using, a very simple model, low resolution model that one shouldn't use to do high resolution regional impact assessment probably or other things, but it can be used to understand basic features of climate. And this model is using the equations that we have derived in this course. So we are using the equations in the pressure coordinate system. This model is based on the pressure coordinate system. In principle, it's a small deviation, maybe coordinate system that is pressure divided by the surface pressure, but in principle, it's similar to a pressure coordinate system. So essentially, this model contains this equation here, the hydrostatic equation, contains the momentum equation, probably adding frictional terms in the boundary layer, and this will be an important part. So this is something that's not included here, plus the continuity equation, plus the thermodynamic equation for the pressure coordinate system. This is the set of equation that is solved. Plus one additional thing, because we need to include moisture explicitly. So the right hand side of this equation has the specific humidity derivative here that we, in principle, then we abbreviate by this Q. But it's important to understand in a model then where, due to rising motion, where we have moisture, and due to rising motion, we may expect condensation. So all climate models or weather forecasting models, the minimum they also should do is they should carry another variable that is for the specific humidity, a time equation, prognostic equation for the specific humidity that can interact then with the thermodynamics. That is what this model is. I won't discuss this in details right now because it would take too long. And then, of course, as you can imagine, such a model is discretized in time and in space. But in this, like many models of the atmosphere, they are posed in this pressure coordinate system because we assume the validity of the hydrostatic approximation. But we also we don't discretize this in physical space, but in spectral space. So this model is also a spectral model, like many climate models. There is a Fourier transformation when integrating this model that at every time step transforms all the fields into spectral space, and then that's discretized in terms of wave numbers, and then the model is integrated. But in principle, that are just techniques that you may or may not discuss in your numerical methods course. So that's this model that I'm using. It uses this equation, plus it needs to add some physical parameterizations. We have said this already. There has to be something in the boundary layer The boundary layer processes have to be added to this model. Radiation has to be parameterized. And I think Adrian will give a course in the second term on physical parameterizations in climate models also. He will discuss some of these parameterizations that have to be added. We call them physics. So there's usually the distinction between a dynamical core, which are all these terms that are easily understood as a Navier-Stokes equations or the Euler equations even. And then there are the physics, and the physics are of course very important. So they are radiative processes. There has to be the condensation processes, evaporation processes, surface friction, and everything that we may think is important. And of course, in order to integrate such a model, we need also boundary conditions. So this model, it's in the zonal and meridional direction, it's global. So we don't have lateral boundary conditions, but at the lower and at the top, there have to be boundary conditions. Now the top boundary condition is easy. In a pressure coordinate system, we can just say we integrate until the pressure is 0. So all the atmosphere is included in principle. But the lower boundary conditions, there we have, of course, our surface. Now, and that would be normally would contain sea surfaces, land-sea contrast, the oceans, and so on. So over oceans, there are treatment of many processes may be different than the ones over land. So over ocean, we have full water availability, but over land, that's not the case. Over land, for example, evaporation may be influenced by the fact that we don't have a completely saturated soil and so on. And over land, we have orography and we have vegetation that can modify the equations and so on. But in this model, we keep it much more simple. We say we remove all land surfaces. We just have ocean. So we just prescribe a sea surface temperature at the lower boundary. No orography, no trees, nothing, just ocean. Plus, even more simple, we don't prescribe a realistic ocean with realistic temperature distributions. No, we say the temperature distribution we impose is completely zonally symmetric. So there's no change if we go from, let's say, in this case, from 180 east to 0. There's no change in this boundary condition. So do I have it here? Yes. So the sea surface temperature boundary condition would look like this in the annual mean. It's warm at the equator and it's cold if we go further to the exotropics. This can be done. And then it was already interesting for us to understand what parts of the general circulation of the atmosphere that we observe can be explained already by this very simple setting, and what parts cannot be explained. What things that we observe if we look at the real climate can be explained by such a simple setting. Now, if we look at the solution, the long-term mean solution, they look very zonally symmetric as they should be. So if we look at the precipitation annual mean precipitation climatology, we see things that are quite expected. We see our extratropical storm tracks, where we have the westerly winds and this low pressure. This is the surface pressure here. So we have a low pressure regions in both hemispheres, symmetric. Then we have a region with higher pressure in the subtropics. And we have where it's dry. And then we have again a region of increased rainfall closer to the equator. Now, as you can see here, and this is something that happens in many models, even though the equator will be probably nearly the warmest region, we have what we call this double ITZZ. So we get one convergence zone north of the equator and one convergence zone south of the equator. It turns out that the one north of the equator, also in the real world, if you do a zonal average of rainfall and calculate the annual mean, is more powerful than the one in the southern hemisphere. The reason for this is in principle still under debate. It's related to the mean, also to the mean temperature distribution between northern and southern hemisphere. And one of the more canonical explanations that is most accepted is that it's actually an effect of the Atlantic meridional overturning circulation, which transports, you will discuss this in the oceanography course, that transports permanently heat from the southern hemisphere to the northern hemisphere and makes on average the northern hemisphere to be warmer than the southern hemisphere. So there's some hemispheric asymmetries here that could have been removed also. I could have said, oh, I want to have a setting that is even simpler. I just use completely symmetric SSTs also in the north-south direction. But that is at least a more realistic aspects here. And then in terms of surface winds, we get what we expect in the tropical regions. We get our trade winds. We get our northeasterly and southeasterly trade winds. We get our westerly winds in the storm tracks. And then we get a more complex picture again as we go to the polar regions. And if we look at the upper level winds, we remember we had our jets. So at the upper troposphere, we find very strong winds, positive winds. So winds that blow from the west to the east, almost everywhere. But in the tropics, we have this, what is called tropical easterly jet. So we get the opposite wind direction. So some features that can be observed are there. Now, this is the picture that you get if you look at a long-term average of this model. If you look at one time snap of this model, you would see waves. So there would be waves, propagating waves, Rossby waves, equatorial waves, everything. There would be rain bands that move. But if we do the average, there should not be any favorable region in the zonal direction for rainfall. Everything should average out in time. But if we look at a particular time snapshot, we would see that there are structures. So there are waves that transport energy from the south to the north and so on. And moisture is transported around and so on. If we look at every time step, only that in the mean, this is averaged out. This is interesting to look at already. If one makes a mistake, it happens sometimes that one can make a mistake. If one doesn't impose any initial perturbations, one has a completely zonally symmetric initial condition and the boundary forcing is completely zonally symmetric. It may happen that these waves just don't develop, but then you get a completely different mean state. So a completely laminar flow solution can also be the solution of this. But if you start with some initial small perturbation, those will grow because we have all our instabilities that we have derived, the baroclinic instabilities and instabilities in the tropics. They will all be present, and so our waves grow in principle. And we get a very, very nicely propagating waves here. But on average, there should be no preferable situation. There's no reason why we should have an average trough somewhere in the exotropics, like we have in the case where we have mountains, land-sea contrast. Then we have seen there are strong deviations from the zonal mean, but they are driven by land-sea contrast and mountain distribution. So this would be our, what we call a control simulation. But we can understand many things already from this control simulation. But now we want to understand what is the adjustment to an imposed heating. So we perform another simulation where we add on top of this state, where we add on top of this boundary condition, of this lower boundary condition, that is just a zonally symmetric sea surface temperature distribution. We add on top of that a warm sea surface temperature perturbation. In this case, it's just a Gaussian distribution with a 2 degrees anomaly. So that would be something like a typical El Nino event. Not very strong, but something like this. And we put this somewhere. The position is completely arbitrary because it doesn't matter where it is. We just put it in the middle of the domain. But it's anyway, we have periodic boundary conditions. So there's no... But of course, now we have given an asymmetry to this. We have put this perturbation there. And we do two simulations, one with this perturbation added to this, and the other simulation without this. And we look at the difference. So if we look at the difference, for example, then in sea surface temperatures, we would just see this pattern. But if we look at the difference in other field, we will see the adjustment of the model to this sea surface temperature perturbation. So the response, we know a little bit what we expect already because we have kind of studied in a much more simplified setting. We have studied the response to heating in the Gill model in the tropics. What should happen in the Gill model? And the response actually looks a little bit like that. Let's concentrate first. So these are the responses that we see to this imposed sea surface temperature perturbation in this model. The field that is shown here is the upper troposphere velocity potential. So the gradient of this field, so the gradient of this field psi gives us our velocity vector, our divergent velocity vector, u and v, but they are psi, so they are related to the, let's say, you write it like this. These are our divergent winds. So what is happening is that, and there's a sign convention to this. So where we have the heating, which is where the SST anomaly, the sea surface temperature anomaly is, we get the rising motion, the air hits the tropopause, and the flow will move outside here. So we get this, what we expect is this divergent motion induced by the fact that we have the tropopause somewhere. And in this other region, we get exactly the opposite. We get the compensating converging flow. So here now, so this is a little bit consistent with what we have discussed before. There should be, when we have upper level divergence somewhere, there should be compensating upper level convergence in another place, in other places. Then, and this is something that we will discuss in one of the next lectures, the other field we can look at is here the stream function. As you know, the stream function is related to the vorticity field and the rotational wind. So the wind that is governing the curl of the wind. This is the stream function field. And that has an interesting out-of-phase relationship with the with the velocity potential field here. So there's an interesting relationship between these, very systematic relationship between these two fields. A relationship that we will discuss in one of the next lectures, a very important relationship that is also valid in the tropical regions. But that is not, it's not so crucial that we understand this here. Another field that we can check out here is the surface pressure. So in the region where we have the warm sea surface temperature perturbation, we have a low pressure. But then this low pressure extends to the north and to the south, and we get something that resembles like our Rossby wave gyres, so the Rossby wave, equatorial Rossby wave solutions may be identified here. Whereas on this side here, we may identify a solution that resembles more the Kelvin wave. If we look now at the wind field, we get that at the surface, exactly the opposite is happening to what is happening in the upper levels. This is now just a zonal wind. So at the surface, we have converging motion into the warm sea surface temperatures and into the heating, into the maximum heating. So we get converging motion, exactly the opposite compared to the upper troposphere. We have discussed this, or we have discussed this in principle already in a sketch that we have done here. So where we have the warm anomaly at the surface, we expect converging motion, then the air rises and has to diverge in the upper levels. It has to be exactly the opposite. So that is the case in this model simulation. But the interesting thing is, if you pay attention, careful attention here, then the fact that there is this shear of the zonal wind in the y direction, that will provide us a vorticity field. Because you know the vorticity would be, one component is du by dy with a minus sign, where the other is dv by dx. But let's say for the time being, we assume that the velocity fields are dominated at the surface by the zonal wind. So then this zonal wind here would give us a vorticity in this region. And also this zonal wind adjustment will provide us a vorticity in that region. This is very important to note. Then we look at the rainfall. We are really interested in the rainfall adjustment, which is shown here. So in the region where we have the positive sea surface temperature perturbation, we get a positive rainfall anomaly. This is what we expect, right? This is what we have discussed. But then outside, it's weaker, but something interesting is going on. There are strips with decreased rainfall, as by the blue colors here, and strips with increased rainfall. So that looks very symmetric, strangely symmetric. And as it should probably, this is very well correlated and spatially correlated with the vertical velocity, in this case here, in the pressure coordinate system. So the omega vertical velocity, dp by dt. The correlation between these two fields is extremely high. Now this is omega taken at 850 hectopascal. There is a reason for this. We could have taken omega also at a higher level, maybe at the mid-troposphere, but we take it a little bit at the lower troposphere. But they are still extremely highly correlated. So our assumption that the vertical velocity is very much related to the diabatic heating induced by the convective condensational heating that would be highlighted by this field, is very well fulfilled. So So this equation here, which we have used already many times, this equilibrium derived from the thermodynamic equation that the heating, that the convective heating, or any type of heating, but let's say for our purposes, in this wet tropical regions, mainly convective heating, so large-scale heating, is compensated by this cooling term, by the diabatic cooling term, mainly because all other terms, the horizontal advection term, the time derivative term, would be small. So this equilibrium seems to be very, very well fulfilled, even if we take the vertical velocity not as an average, but just take one level, then this seems to be spatially very well correlated. So that seems to be fulfilled. They are very well related, these two fields. But now we want to understand now, how can we explain this? Because in this region here, we can explain the increased heating by the destabilization, by having the warm patch, and then we get the compensating vertical motion. But what is happening in the other regions here? Now, one field that we can immediately look at is, and that fits to some extent well, is this upper level divergence field. So we get the positive upper level divergence above the heating. So the air is flowing out there. So that is consistent with what we expect. And then in the surroundings, we see this negative divergence, so convergence. So that is what we expected is kind of fulfilled. It's a more complex picture. And that is somehow correlated to our vertical motion and rainfall adjustment. Because what's happening is, if we have upper level convergence, again, due to the continuity equation, the air has to sink and cause a negative vertical velocity in the pressure coordinate system, or positive. And then that should influence the rainfall according to our equilibrium. So there's some relationship, but it doesn't look like a very close match. On the other hand, of course, the whole aim of this is then to guess that it may be the Eggman pumping that is so important. Now, we have derived what the Eggman pumping does. So in principle, we have seen that we get, if you can work out, this is a positive du by d, this is a positive u, but it decreases with meridianal direction. So that is a positive vorticity that we get here in the region, let's say, between 10 north and 30 north. And we get the opposite on this side. So we get a negative vorticity here. So you can guess that rainfall adjustment actually fits quite well with what we see, that vorticity adjustment and imposing what we know from Eggman pumping. So positive vorticity would lead to rising motion. So we get indeed increased rainfall in this strip. And the anticyclonic flow here would, through Eggman pumping, cause sinking motion. And so we get the suppressed rainfall. So that should fit quite well. Now, the models use different kind of boundary layer schemes. It could be the scheme that we have derived in the last lecture, this kind of this scheme that makes use of a closure analogous to the molecular frictional dissipation. So this flux gradient theory. But actually the model that I'm using is using something much simpler in some respect, which is called a drag coefficient approach. So you say the surface friction in just the Eggman layer, that is expressed in these equations here, is not done by this vertical exchange of momentum. It is, but in the model it's parameterized in a much simpler way. And this is called drag coefficient approach. So you say that there's a drag that is proportional to the wind, to the U wind that is caused by in the planetary boundary layer, which is just in this model, just one layer. So it's a very simple model. And that works also for both components. But then it's a little bit more complicated in the sense that there's a typically used a nonlinear term. So it's not only this drag, but then there's a coefficient that again depends on the velocities and on the square root of the velocities. And then there's again, a constant term here. So this is a commonly used drag coefficient formulation in climate models. But what it does, if you think about it, what it does, if we write down these equations in the boundary layer, and if this drag coefficient is 0, our wind would be the geostrophic wind. So what this does is it perturbs our wind field to deviate from the geostrophic wind. So exactly what we have in our Eggman layer in principle, only that this formulation is a little bit simpler. And you can solve this. So we solved this by imposing from our model simulation for the free atmosphere. We took the wind field, the geostrophic wind field, and related to the geopotential solution. And we calculated, so what would be in this model, the Eggman pumping effect on the vertical velocity. And the outcome of this is this field here. So this is the Eggman pumping induced vertical velocity at the top of the boundary layer, which is about 850 hectopascal in the model. And if you compare this field, which looks very, very symmetric, right? Extremely symmetric. If you compare this field, with the real observed, model observed vertical velocity, they match extremely well. I mean, a little bit less symmetric, but otherwise extremely well matching. Apart from the region where obviously we cannot explain the vertical velocity by Eggman pumping, which is the region where we have imposed the sea surface temperature perturbation and the heating. But outside, there's a very well match. So that means, at least in this model simulation, the vertical velocity field and the rainfall adjustments are very much governed by Eggman pumping in this model. With some deviations, if you look carefully, then here that would suggest that at the equator, we get strongly suppressed rainfall, and then off the equator, no, this is omega. So at the equator, we get rising motion here, and off the equator, we get strongly sinking motion because this is omega. Remember, this is omega, the pressure vertical velocity, so we have to switch sign. So suppressed sinking motion here and rising motion here. If we look at what we observe is, yes, that's the case, but there's some, there's some tendency to get also here some sinking motion. It's not so symmetric, and then maybe some increased here. So that could be related, this deviation could be related to this very strong sinking motion induced by the upper level divergence field, upper level convergence field. So it seems that these two mechanisms, they act together, but if you kind of work out, you can, for example, calculate the correlation of the omega field, of the full simulated omega field with both, with the Eggman induced vertical velocity and with the upper level divergence field. You will find that the correlation with this field is very high, like almost 70%, more than 70%. And the correlation with this field is still there, maybe 40, 50%, but much less. So the rainfall and vertical velocity field is mainly impacted by the Eggman pumping in our model simulation. So Eggman pumping seems to be a very important mechanism, how remote regions can be influenced by a localized heating anomaly, for example, in the Pacific or in other regions. And so this mechanism, for example, may be relevant for adjustments to the El Nino type sea surface temperature perturbations and heating anomalies in the South Asian region or in the African region, and so on. So this is about what I wanted to say today. There are no exercises in this lecture. So in the next lecture tomorrow, we will discuss some more features of the general circulation that we have touched on today again, but we will try to make a systematic approach by trying, not like in this model simulation where we remove all the zonal asymmetries, but we will use another approach. We will try to understand what can we understand if we do an integration in the zonal direction. And we look at perturbations, deviations from this zonally completely symmetric situation in that case. What can we understand? So that will be discussed in the next lecture, how we can understand the general circulation by using a completely zonal average. So we will discuss in that framework then also the Hadley circulation, which is a very important circulation. We have discussed already the Walker circulation in the Pacific briefly, but we will pick up on that again in future lectures. But we will discuss in next lecture the Hadley circulation that is present in the tropics, and then in the exotropics, how for example, the westerly winds, the strong westerly winds in upper levels can be explained by these simple considerations. Okay. So see you tomorrow then. Have a good day. Bye.
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 Bye.